Welcome to videos on ADCs. So this is the fourth part. In this video, we shall see analog to digital conversion techniques. There are different techniques to convert the analog voltage to the digital form. So one of the form is DAC based ADCs. So we'll be using digital to analog converter to realize analog digital conversion. And then we have flash ADCs, and we have integrating ADCs, and then we have very recently the advanced one, the sigma delta conversion ADCs. So let us first look into what is this DAC based A to D conversion. So as the name itself indicates that, so there is a digital to analog converter required to realize analog digital conversion. So this is the block diagram representation of a DAC based ADC. As we can see here, there is a DAC here, and we have a register which is acting like a counter, and we have a start of conversion, start the conversion process, and we have an end of conversion pin which is going to indicate the conversion is done, and we have B1 to Bn as the output of ADC, and we need a reference voltage for this DAC, so that is what is this V reference, and the output voltage of the DAC is compared in a comparator with respect to the input voltage. Now this comparator, which is an op-amp, will going to give a signal to this register, which is usually a counter, whether to do the counting or stop the counting. Now I can see, as we are seeing, the comparator actually compares the output of the DAC to the input voltage that is to be converted from analog to digital. If the comparison is positive, so this will be stopping. If the comparison is negative, it will be keep on allowing the conversion. Okay, it will be keep counting. So let us see the detailed working of this DAC based ADC in the coming slides. So this DAC based ADC consists of a register which is a clock generally, and there is a DAC required, and there is a comparator, and of course as usually for a ADC we need to have a start signal. There is an end of signal that is coming out. The input voltage we are applying, this V reference will actually go to this DAC. So let us see, this A to D conversion can be accomplished by using a DAC, a suitable register to adjust the DAC's input code until DAC's output becomes within plus or minus half LSB of the analog voltage. So we know that in the previous INL and DNL expression, so we'll be keep changing the output voltage from one level to other level, so as long as there's a difference of half LSB in the input voltage. We shall see the understanding of this particular statement in the coming slides. The code that is the code that achieves this is the desired ADC output, because we'll be allowing the ADC to function as long as its difference is coming out to be half LSB plus or minus half LSB. The code that we get from this, so as we can see here, this is the code that we're going to get. So this code B1 to Bn actually represents the digital output voltage for the given analog input. This technique requires a suitable logic circuitry to direct the register to perform the code search on arrival of a start command. So the meaning of code search is, suppose if you are given some input voltage, and if you start that start of conversion, that is, if you say the ADC to start the conversion, now this ADC will start operating, and it is searching for that code where it should give the output as a corresponding digital output for that given input voltage. The code search is actually, so it will going to stop whenever that code is appropriately equal to that input voltage within plus or minus half LSB of the input voltage. So we shall exactly take up an example and then try to find out, okay, how does this going to work. So after the code has been searched, so it will give an end of conversion command, and it stops the operation, and it finally gives the digital output. So this is what is the same DAC based ADC conversion. Now let us see the working of this DAC based ADC. The simplest code search is a sequential search obtained by operating the register as a binary counter. So we talked about the code search. So as soon as we give the input voltage and the start of conversion, the ADC is actually looking for a code which is equivalent to the analog input voltage. So that code search can be done using a sequential search, which can be accomplished by using this register as a binary counter. As a counter steps through the consecutive codes, that is from 000, because now this is a n-bit counter, so it will start from 000. So when this 00 is there, and of course we are going to, that will be fed to DAC. This DAC will going to give some output voltage. That output voltage is compared with the input voltage. If that output voltage is less than the input voltage, then this continues to count up. So once it is counted up, it is again compared with the input voltage. If it is still less than this, so this counter is further allowed to count. So this will be keep on continuing as soon as this voltage, as you can see now. So this, just a minute. So the DAC produces an increasing staircase which is compared with the VI value. So this we know that it will going to give an output voltage, because this is like a staircase generator, because you are increasing the input bit by bit. So the output will be like a staircase. So every step will be compared with this V input voltage. As soon as the stair reaches VI or slightly greater than VI, the comparator fires. So comparator is going to give a different output voltage. Then this makes the register to stop the count. When the register is stop counting, so this register is going to give a EOC signal indicating that conversion is done. So the corresponding output of this counter will be read as the digital equivalent of this analog voltage. So that's what we are seeing here. As soon as this staircase is coming from this DAC, as soon as it reaches VI and slightly above that, the comparator actually stops the counter, and it serves an EOC command to notify that the desired code is sitting in the counter. So once this desired code is sitting in the counter, you can read this value, which happens to be the digital equivalent of the analog voltage. Now let us see the working of this. Now just carefully observe all the points here. The input voltage is applied, and the start is not yet given. The clock is applied. So this whatever EOC you are getting is not a valid one. So this is not counting. Why it is not counting means, okay, since we are not given the start signal, and whatever the digital output is not yet evaluated, because we are not yet started the conversion. Of course, we have applied the reference voltage, and since it is not giving any voltage, so there is no output from the DAC, and since there is no output from the DAC, so there is no proper comparison done, so the output of the comparator is not valid. So why all these are not valid is because we have not yet given the start signal. So let us give the start signal. So once I give the start signal here, so now you can see the start signal is given, the clock is applied, and there is no EOC signal obtained yet. Now since the clock start signal is given, clock is given, and this starts counting. So this is a binary counter, this starts counting. When this starts counting, okay, assume that now it initiates from 00 to 0001. So once that is 1, so this reference voltage which is applied will going to give a output voltage as per the digital value here. So this is a DAC. This DAC output will going to be having some analog voltage. So that will be with reference to the applied input voltage. Now if this generated output voltage, if it is less than 1 compared to the applied input voltage, then we'll go to give a signal continue count signal. So this there is a signal which is given to this counter to continue the count. So this counter will be again updating now. So it will not stop. It will going to go for the next stage. When it goes for the next step, So this will be keep on evaluating. So this count will be keep incrementing. For every increment, you're going to get some different output voltage. You are comparing that with applied voltage. If it is less than that, this will be allowed to continue. If it is allowed to continue, it will go for the next count. That is again generating some output voltage, and that is again compared with this. So as long as the output of your DAC is less than the applied voltage, so this process is keep on continuing. So once you are given the start signal, that is enough. So in the next case, we can actually remove the start signal. You have given you have removed the start signal because you have initiated the counter is counting. It is still evaluating. The output is as per the out count here. Still it is less than Vi. Now this allowed to increment the count. So this signal, whatever you're getting from the comparator, is allowing your counter to up count it. It is keep on counting. Now you can see this is still in the loop because this voltage from the DAC, whenever it is compared with this, it is still less than applied input voltage. Now let us see what happens if it is. You can see still it is working. I can say signal is removed here, start signal is removed. It is still not close to this Vi. As soon as it just becomes here, I can see now. Now we are getting the output voltage. Now this V plus is just more than Vi. So why it is more than Vi? Because till the previous state, so we were still allowing the counter to count. When you were allowing the counter to count, so this is keep on incrementing, a stage will reach where this output voltage will slightly greater than supplied voltage. So that's what it is. It is just more than V. So till this point we had some voltage which was allowing the counter to count. As soon as this increases beyond your V, then it stops the signal to count. So there is a stop signal to count the counter. Now this counter stops counting, but it holds the previous value. Now whatever value that was there prior to this increment, so now it is stopped counting. Now the whatever value that is the counter is holding, so is the digital value of this corresponding input voltage. Now we know that this was keep counting as long as this output from the DAC was less than the input voltage. As soon as it becomes slightly more than that, this comparator has given a signal to stop it, and once it stops, so the digital value is evaluated. So that can be noticed by seeing this EOC signal. Now the EOC signal is now made high or low, depending on it will be opposite to the previous value what you had. Now this EOC signal will be generated to make sure that the conversion is completed. Now this way, so we can comfortably have a look at it again back. So I'm starting one. Now here we are not yet given the start signal, so nothing is initiated. So once we give the start signal, this starts counting. So it is going to give a corresponding digital analog voltage that is compared with the input voltage. If this V plus is less than V minus, it will be allowing a signal, it will be giving a signal so that this counter is counting. So this will be keep on counting unless this input voltage or this V plus is less than V minus here. So once it exceeds that V in, that is when this V plus becomes more than V minus at the input voltage, it gives a signal to stop the count. So this whatever binary count we have is the digital equivalent of this binary voltage. So once that happens, so the EOC will be generated to indicate there is a end of conversion done. So the conversion has been completed. Now let us see some of the for 8-bit ADC, assume the clock to Q delay, because we know that there is a counter. So counter will certainly take some time to give the output voltage upon giving the clock. Let us assume that clock to Q delay is 10 nanosecond, and DAC conversion time is 50 nanosecond. Once you give the input to the DAC, DAC will certainly take some time to give the output voltage. Let us assume that that time is 50 nanosecond, and let us assume that the op-amp response time is 10 nanosecond. So if when the input changes at the op-amp will also take some time. So let us assume that that time is 10 nanosecond. It was asked to find what is the maximum clock frequency allowed for proper operation for this ADC, and with 90% of that clock applied, what is the conversion time for ADC? We shall see this